Welcome back. Today we're going even deeper into attention mechanisms, the true heart of transformer models.
We touched on attention in episode 4, but today we're really unpacking all the different types and variants.
Exakt i den morgen til slijking stusimo. Willis. Let's start by reinforcing the core concept. What problem does attention solve?
Traditional sequence models like RNNs process one token at a time and try to compress all previous information into a fixed size hidden state. But this becomes a bottleneck for long sequences.
Attention solves this by allowing the model to directly access any part of the input weighted by relevance. Instead of compressing everything into a bottleneck, you can selectively pull information from wherever it's needed.
The key innovation is learning what to pay attention to rather than treating all input equally or relying on recurrent compression.
Let's break down the taxonomy of attention. First, there's self attention versus cross attention.
Self attention is when a sequence attends to itself. Each position looks at all positions in the same sequence to gather relevant information.
Cross attention is when one sequence attends to a different sequence. This is used in encoder decoder models, where the decoder attends to the encoder's output.
It's also used in retrieval augmented generation, which we'll discuss in a later episode where the model attends to retrieve documents.
Next, let's talk about the mechanics of scale dot product attention in more detail.
You have three matrices: query, key, and value. For an input of dimension D model, you project it into these three representations using learned weight matrices.
The query represents what am I looking for, the key represents what do I contain, and the value represents what information can I provide.
You compute the attention scores by taking the dot product of each query with all keys. This gives you a matrix of scores.
The dot product measures similarity. If two vectors are aligned, the dot product is large. If they're orthogonal, it's zero.
These scores are scaled by dividing by the square root of the key dimension. This scaling prevents the dot products from growing too large, which would cause the softmax to saturate.
Then you apply softmax to convert the scores into a probability distribution. Softmax normalizes the scores so they're all positive and sum to 1.
Finally, you compute a weighted sum of the value vectors using these probabilities as weights. This gives you the output for each query position.
The beauty is that this entire computation can be done as matrix multiplication, which is very efficient on GPUs.
Now let's talk about multi-head attention. Instead of doing attention once, you do it multiple times in parallel with different learned projections.
Each attention head can focus on different types of relationships. One might capture syntactic structure, another semantic similarity, another positional relationships.
Typical models use 12 to 96 attention heads, depending on the model size. The heads run in parallel, and their outputs are concatenated and projected back to the model dimension.
An interesting variant is multi-query attention or MQA. Here, all heads share the same keys and values but have different queries.
This significantly reduces the memory footprint of the KV cache during inference, which speeds up autoregressive generation.
Group query attention or GQA is a middle ground. Heads are divided into groups and heads within a group share KV pairs.
GQA balances the quality of full multi-head attention with the efficiency of multi-query attention.
Let's talk about the causal mask, which is critical for decoder models.
In autoregressive generation, each position should only attend to previous positions, not future ones. Otherwise, the model would cheat during training by seeing the answer.
The causal mask is implemented by setting attention scores for future positions to negative infinity before the softmax. After softmax, these become zero.
This creates a triangular pattern of attention. Position 1 only sees itself. Position 2 sees positions 1 and 2. Position 3 sees 1, 2, and 3, and so on.
Now, one of the challenges with attention is that it has quadratic complexity. For a sequence of length n, you compute n squared attention scores.
This becomes prohibitively expensive for very long sequences. Researchers have developed many solutions.
Sparse attention patterns only compute attention for certain pairs of positions, not all of them.
For example, Longformer uses a combination of local windowed attention and global attention on special tokens. Each position attends to its nearby neighbors plus a few global positions.
Big Bird uses random attention, window attention, and global attention. This reduces complexity from quadratic to linear while maintaining modeling power.
Another approach is linear attention, which reformulates the attention computation to avoid the explicit quadratic term.
Kernel attention methods approximate the softmax attention with kernel functions that can be computed more efficiently.
These linear and kernel methods are mathematically elegant, but in practice often don't match the quality of full attention.
A different approach to efficiency is flash attention. It doesn't change the computation, but optimizes how it's executed on hardware.
Flash attention is I/O aware. It carefully manages data movement between GPU memory hierarchies to minimize slow memory reads and writes.
By fusing operations and tiling the computation, flash attention can be 2 to 4 times faster than standard attention implementations while computing exactly the same thing.
Let's talk about the KV cache, which is crucial for efficient autoregressive generation.
When generating token by token, you compute attention over all previous tokens. Naively, you'd recompute the keys and values for all previous tokens at each step.
But keys and values for previous tokens don't change, so you can cache them and reuse them.
This transforms generation from quadratic in sequence length to linear, dramatically speeding up inference.
The trade-off is memory. For a model with large hidden dimension and many layers, the KV cache can become quite large for long sequences.
Some systems use cache eviction or sliding window caches, where you only keep the most recent K tokens in the cache.
Another advanced technique is windowed or sliding attention, where each position only attends to the most recent W positions.
This bounds the complexity and memory usage, and for many tasks, local context is most important anyway.
There are also hybrid approaches that combine local and global attention patterns.
Now, let's talk about attention maps, visualizations of what the model is attending to.
You can extract the attention weights after softmax and visualize them as a heat map. This shows which positions the model focused on for each query.
These visualizations can be insightful for interpretability, showing that models often learn to attend to relevant words for tasks like coreference resolution or syntactic parsing.
But attention is not the same as importance or causation. Just because the model attended to something doesn't mean it was causal for the output.
Attention is one mechanism among many in the model. The feed forward layers, residual connections, and layer norms all play important roles too.
Speaking of which, attention outputs go through residual connections. The attention output is added back to the input, allowing gradient flow and preserving information.
This residual stream is like a highway of information flowing through the model, with each layer reading from and writing to this stream.
So, to recap, attention mechanisms allow selective information gathering. They come in many forms, including self attention and cross attention. Scale dot product attention with multi head variance is the standard. Causal masking enables autoregressive generation. Optimizations like flash attention and KV caching make attention practical. And sparse attention patterns handle very long sequences.
Next episode, we're diving into pre training versus fine tuning, the different training strategies for LLMs.
Thanks for sticking with us through this technical deep dive.
Until next time, keep learning and stay curious about AI.